In today's lecture, we're going to talk about sampling in research, a concept that almost every student uses, but very few truly understand. Sampling is at the heart of research, because in real life, we rarely study an entire population. Instead, we rely on samples to make conclusions about larger groups. But here's the important point. If your sample is poor or biased, then even the most sophisticated statistical analysis will give misleading results. That's why understanding sampling is essential for undergraduate students, MBA learners, master's students, and PhD researchers.
Don't worry. In this lecture, I'll explain everything slowly, step by step, and using very simple real-life examples.
By the end of this video, you will clearly understand what sampling is, why it is used, common sampling errors, and how to avoid mistakes that weaken your research. Before we begin, if you don't want to miss future videos that simplify research methods, statistics, SPSS, and data analysis, please subscribe to our channel, like this video, and follow us for regular updates. Now, let's get started with sampling in research.
Let's start with a very important question. In research, do we usually study everyone? The answer is no. In real research, it is almost impossible to study the entire population. That is why sampling exists. Sampling means we study a small group of people and then use the results to understand the larger group. Think of tasting soup. You don't drink the whole pot, you taste one spoon. That spoon is your sample. The whole pot is the population. If the spoon is mixed well, you can judge the whole soup. That is exactly how sampling works in research.
Now, let's clearly understand four basic terms. First, population. A population includes all individuals or items you're interested in. Example, all undergraduate students in a university, all customers of a company, all households in a city. Second, parameter. A parameter is a numerical value that describes the population. Example, true average income of all households, actual percentage of satisfied customers. Third, sample. A sample is a small but representative part of the population. Example, 300 students selected from 10,000 students. Fourth, statistic. A statistic is calculated from the sample. Example, average GPA of the 300 students.
You might be thinking, why not just study everyone? Good question. There are four main reasons. Reason 1, population size. Some populations are extremely large. Imagine studying all social media users, all consumers in a country. It's not practical. Reason 2, cost. Research costs money. Printing surveys, hiring researchers, travel, it all adds up. Reason 3, time. Data collection takes time. By the time you finish, the situation may already have changed. Reason 4, access. Some people are unreachable, unavailable, or unwilling. Because of these reasons, researchers rely on sampling. Sometimes sampling is not appropriate. In such cases, we conduct a census. A census means collecting data from everyone. You should take a census when the population is small, example, all teachers in a small school. Every case is important, example, quality inspection of aircraft parts. Credibility requires full inclusion, example, national population census. Census gives complete information, but it is rarely feasible for large populations.
Sampling is extremely useful. First benefit, efficiency. You save time and resources. Second benefit, generalization. With proper sampling, you can make conclusions about the population. Third benefit, accuracy. A well-designed sample can give results almost as accurate as a census. Example, election polls survey only a few thousand voters, yet predict national results. That's why sampling is central to research.
Now let's talk about sampling error. Sampling error is the difference between the true population value, the value obtained from the sample. Example, true average income equals 5,000. Sample average income equals 4,800. The difference is sampling error. Sampling error occurs because different samples give slightly different results. Important point. Sampling error is not a mistake. It is natural and unavoidable. The key is to measure and minimize it.
Sampling bias is more serious. Sampling bias happens when some members have a higher chance of selection than others. Example, conducting an online survey about education. Older people may be excluded. The result? The sample does not represent the population. How do we reduce bias? Use random sampling. Give everyone equal chance. Bias affects validity, so it must be avoided.
Now, let's understand standard error of the mean, or SEM. SEM tells us how much the sample means vary around the population mean. Key idea: smaller SEM equals more accurate estimate. SEM depends on sample size. Example: sample of 30 equals higher SEM. Sample of 300 equals lower SEM. Larger samples produce more stable results.
The central limit theorem is very powerful. It says, when sample size is 30 or more, the distribution of sample means becomes normal, even if the population itself is not normal. This allows us to use confidence intervals, conduct hypothesis tests. CLT makes inferential statistics possible.
Now let's understand the central limit theorem using a very simple and practical example shown on this slide. This is one of the most important ideas in statistics, so I'll explain it slowly and step by step. Let's start with the left side of the slide, which shows the population. Here, the population is all university students. The variable we are studying is hours studied per day. Now notice something important. Most students study 2 to 3 hours per day. Only a few students study 8 to 10 hours per day. Because of this, the population distribution is right-skewed. That means the data is not symmetric. It is not normally distributed. And this is very common in real life. Most real-world data, income, study hours, expenses, does not follow a normal distribution. Now let's move to the middle part of the slide. Here, we are not studying the whole population. Instead, we randomly select 30 students, calculate the sample mean each time. This process is repeated again and again. So we take sample 1, calculate mean x1. Sample 2, calculate mean x2. Sample 3, calculate mean x3. Each sample has at least 30 observations. For example, sample 1 mean equals 3.8 hours. Sample 2 mean equals 4.1 hours. These sample means are different, but they are all estimates of the same population mean. Important reminder, we are not plotting individual students anymore. We are plotting sample means. Now let's look at the right side of the slide. Here, we take all those sample means and plot them. Something very interesting happens, even though the population was skewed. In another video, we will explain skewness and kurtosis in simple words with examples. The population was not normal. The distribution of sample means becomes normal, bell-shaped. This is the central limit theorem. The center of this distribution is the population mean, mu. The spread of this distribution is the standard error, not the standard deviation. As we take more samples, the curve becomes smoother. The estimates become more stable. This happens only because sample size is large, n is greater than or equal to 30. The central limit theorem tells us, even if the population distribution is not normal, the distribution of sample means will be normal when the sample size is sufficiently large. This is why we can use confidence intervals, perform hypothesis testing, apply t-tests and ANOVA. Without the central limit theorem, inferential statistics would not work.
This slide shows a simple example of sampling error. Suppose our research hypothesis is that the average textbook price in a university is $100. This represents the population value. Now, instead of checking every textbook, we select a sample of textbooks. From this sample, we calculate the average price, and we find it is $85, not $100. This difference between the population value and the sample value is called sampling error. Sampling error happens because samples are smaller than populations, and different samples can give slightly different results.
This does not mean the research is wrong. It simply reflects natural variation in sampling. We use the standard error to measure how accurate our sample estimate is.
This slide explains an important step in research, defining the population. Before we select a sample, we must clearly decide who exactly our study is about. First, we specify boundaries. This means defining things like age group, location, time period, or specific characteristics. For example, instead of saying students, we say undergraduate students enrolled in business programs in 2024. Second, we clarify criteria. This means clearly stating who is included and who is excluded from the study. This avoids confusion and improves consistency. Finally, we align the population with research goals. The people we study must directly match the objective of the research. If the population is poorly defined, even good sampling techniques will give weak results. So remember, clear population definition is the foundation of good research.
This slide explains the idea of a sampling frame. A sampling frame is the actual list from which we select our sample. In simple words, it answers the question, from where exactly are we choosing our respondents or units? A good sampling frame must be a complete list of the target population. This means every member of the population should be included, and each member should appear once and only once. Common examples of sampling frames include membership lists, databases, and client or customer lists. If the sampling frame is incomplete or has duplicates, the sample will not be representative, even if we use random sampling. So remember, a strong sampling frame is essential for accurate and reliable research results.
This slide explains sampling frame errors, which occur when the list used for sampling is inaccurate. Remember, the sampling frame should include all population members and only population members. There are two common types of sampling frame errors. First, over-registration. This happens when the sampling frame includes people who do not belong to the target population. For example, if we are studying university students, but our list also includes non-students, then those extra names create over-registration. Second, under-registration. This happens when some actual population members are missing from the sampling frame. For example, if some enrolled students are not listed in the database, they are excluded from the chance of being selected. Both over-registration and under-registration are problematic because they reduce the representativeness of the sample. Even if we apply random sampling correctly, a flawed sampling frame will lead to biased results. So always remember, a complete and accurate sampling frame is essential for reliable research.
Now, let me ask you a question. Can you think of a real-life example where some people might be missing from a sampling frame? For example, imagine conducting an online survey. Who might be left out? Or think about using a school or company database. Are all relevant people always included? Take a moment and think about it. Share your example in the comment section below. In our next video, we will discuss the different types of sampling and explain how sampling error and bias can be reduced to obtain accurate results that can be generalized to the population. Don't forget to like the video, watch till the end, and subscribe to our channel.